So, hello everyone. So, welcome again. So we'll be talking about the RIOS pattern classifications and microprocessor pattern analysis. This is actually joint work by a large group of us. I'm just, the representative here, speaking the work of very hard work from very our diligent, team members. Wei Liang and Yao Yue, and also Dr. Liu and Crystal and some other people. All right, so why we're interested in microprocessor pattern research or pattern analysis? So as I said in the very early this morning, so RISC-V is a open ISA, so the spec is complete open, it's free. But once you get into the implementation, get into the microprocessor, getting into the business side, there will be a lot of potential pattern infringement and litigation concerns regarding the implementation itself. And also, this is the modular ISA, like what Calista mentioned. Now, also, this is very simple, so which means user can develop lots of new ISA extensions. And so new ISA extension by itself is also a big concern. The instruction by itself is a concern. And also the microarchitecture, right? So we'll show why this tool is very important later. So so when we talk about the patterns, lots of people are talking about the business, right? So what we're looking at is really for people who are really trying to build RISC-V processors, build implementations, especially for commercial products. If you're a company building a RISC-V processor, and you definitely need to look at what potential patents your processor might infringe and or might have some patent potential litigation problems. And even for us, for open source organizations, we're trying to open source our design. We still have to understand if our current open source design has overlapped or has some of the ideas shared by other patents from other proprietary implementations. So, so our goal here is really trying to, systematically to looking at different ISAs, not just one single ISA, but pretty much the majority of the microprocessor implementations on the market, including both SIX and RISC, and also some major ISA instructions. ARM is definitely one of the things we're looking at, and this is actually what we're trying to update with this talk. And also what we're trying to understand really the heat map of the patterns in certain technology, right? So if you do a microprocessors, you can look at your competing or very related companies. Have they already done a microprocessor implementation in some certain areas? Where are those potential IPs? So really, for example, build up a risk heat map, right? Some areas you should avoid, some areas you should strengthen. Essentially, for us, we're kind of more like a nonprofit organization, research organization. What we're trying to do is trying to publish our results and also our methodology to the community for free. So everyone is encouraged to use this methodology. So that's our motivation in general. And so when we start looking at this, microprocessor has been almost half centuries, right? This is kind of modern microprocessors. So there are lots of instruction set architecture out there, and also there are popular ones, there are not unpopular ones, but still have patents that are still legit today. So in the very beginning, we start with MIPS, right? So this is kind of coincidentally last year. We had a chance to really look at, what are MIPS microprocessor patents, what are remaining ones, and also we got a chance to talk to our, very excellent partner with Imagination, one's own MIPS, about, consulting them on, kind of like the patterns and landscapes. And later, we decided because, we have to face reality, right? So ARM is the pretty much dominant RISC processor on the market. There are lots of patents, ARM has filed or acquired, so there's no point ignore them. So we start extending our work just a couple of months ago after starting the MIPS patents. And as a methodology, we start with the US patent first. It's not just like the China patents, not like the Euro patents. We're starting with the US patent. This really corresponds to most of the companies, how they do the patent works. So lots of companies, especially in the US, usually, in my past companies I am associated with, they usually file US patents first, and sometimes simultaneously will do the patents in Europe as well, and then gradually, spread out around the world. We by looking at the U.S. patent, there's a very good, it's a very good pool. So it's just very representatives. Most of new technologies are pretty much it's from the U.S. patents. So when we start looking at the MIPS or ARMs, we're kind of basically picking all the patents they filed across their lifetime. Right? For MIPS, their company has been sold 7 times, but for ARM, still very much alive. So we're kind of starting from early 90s to for ARM is early 90s, for MIPS like 1984. That's the kind of very early the incorporation of the MIPS to today, right? So pretty much MIPS has been pretty much, I wouldn't say belly up, but it's kind of survived in some certain form. So pretty much to really up-to-date result. We're kind of using the public databases. This is kind of Google patents and also the patents from USPTO office. So if you're looking at the patents, right, so MIPS is kind of really moderate. So when we did that first, we think it's really manageable, right? This is only around 500 patents, and also in pretty much half of them pretty much almost expired. So the only active patents are not very large. But then we start like looking at ARMS. Oh Jesus, they're kind of like more than 4,000 patents, even including the still valid ones. There's still 3,000 of them. So assuming we're gonna extend our work to x86, which is kind of another dominant ISA, and so we'll see this number close probably to 10,000, something like that. So, but just for Wi-Fi, there's a huge amount of efforts behind this. So we're spending, burning up the mint oils, even last night, right? So just checking out the data is really hard work, right? So to begin with, so there are patterns that's being expired or patterns still active. So I think the methodology for us is first, we're just trying to, the expired pattern in most of cases, some cases does not matter. Just when we're trying to look at the ARM patterns, we're trying to reduce our scope. What we did was really trying to, looking at what active patterns. As you can see, for most of the MIPS patterns, for almost half of them, are still active. But a very large portion of them can already expire. This is really corresponds to the MIPS company, the MIPS ISA, MIPS ecosystems. The system's pretty much, I wouldn't say going away, but it's kind of not in its the peak time, not in its heyday. But ARM, on the other hand, there are lots of them, over 70% of ARM patterns are still legit, still valid. There's still quite a big number of patterns that are falling. So this is really in the ARM kind of extending the high performance, the server world, still really seeing hundreds of patterns that are still pending. So those are the things we should really pay attention to. Okay, next slides. So when we were looking at the work on our patterns, here are actually the things we're looking at. So we're looking at the pattern assignment, who actually own the patterns, the still active pattern, because pattern usually will be sold and will transfer to another company. But we're looking at who are actually owning them, right? And also major assignees and owner of the most active patterns, and also application and grant rate. So this is also very, if you look at this across time, you'll see how active the company will be, how active the technology will be. It's also a very interesting metric to tell if this is something you should really worry, right? So it's down the road. And so we're actually looking at the number of patterns that will be expired in the upcoming years. You will see that's kind of more like what I would call like a reality check. Although the good news is some patterns will expire, but that's only a very small portion of that. It's a kind of recurring theme for many other patterns. And also trying to gauge how good the quality of the pattern is also very challenging. So for us, to be honest, we don't really have a very good metric just telling how useful the pattern is, but we're kind of using some statistic metric here. Would like to hear more feedbacks on this to see how good the pattern are. So what we did here is we're trying to look at the citation count and also number of claims. So the more claims, not necessarily more claims, but citation means if this patent has been referred by some other patents or other applications, we'll assume, the patent is, people are actually looking at it, so it has a higher quality. The last is kind of what we're begin looking with KWM altogether is the litigation cases, right? The litigations with the MIPS and ARMS. So those are very interesting things that happen in real life when people are kind of fighting, on the business side. And these are the kind of, the things people mostly worried, right? So we still have some, well, there are some open public databases, trying some proprietary databases, but this is the kind of recurring theme across all the patents studied. But looking at them will be very interesting. Okay, so first of all, let's look at in the existing pattern classifications, right? So when we look at the patterns, their pattern are classified by PTO office. Right? This is their US way, their international IPC version. There's also CPC version of it. They're kind of very they will say very similar. One is more has more little bit more more details and more subcategories than the other ones. But they're kind of really sometimes I will say is from just from technical perspective. If I want to build a product, want to see if my product has some potential patent infringement from certain area, it's actually a little bit hard for us to just by looking at the categories and looking at all the patterns. So to be honest, for most of the people or when we're trying to do the search, we just use free text search. This is not very effective. So when we start looking at these patterns, let's look at the IPC first. Let's more like the international ones. So this is kind of like a top 10 categories among all the active patterns from, I think this is for both MIPS and ARMS. ARMS in the purple colors, MIPS in this the green color. You'll find a trend here is lots of patterns, active patterns can fall into a 1 or 2 categories, or the kind of really cluster just to something, program control, right? So if you just if you build microprocessor program control, yeah, there could be a lot of things related to program control. What does that mean, right? Memory allocating, right? This is more like a software term, but is that tied to specific component or specific parts in the microprocessor? Actually, it's actually not very clear. So we would say this is a lot more general. So when you have a classification methodology, have all the patterns fall in single 1 or 2 categories, and I don't think it's the best we can get, right? Similarly, if you're looking at the CPC, that's kind of the two systems kind of depend on one on top of each other, right? It's kind of joint development by the EU and the US PTO office, right? So they have more specific and more details than the IPC. They have subcategories of CPCs, but still, if you're looking at this, right, it suffer from the same problem, have very similar issues with majority, like very large portion of the patterns fall in the single categories or 1 or 2 categories. So it's, well, I would say it's really general. So when we start by looking at this, we decide, we probably need at least from, a computer architect perspective, at least from people who are trying to build real products perspective, we really need a something new, right? So that can really, be more informative when we're doing the pattern classifications. So then this is kind of from, our, we'll talk about ideas. The ideas is we're trying to look at from domain experts perspective. So I'm a CPU designer and the rest of my team are CPU designers, and we train people to build a product. So what we did here is we're looking at basically a kind of pretty much taking from a Berkeley graduate courses. This is kind of how when we're teaching, computer architectures, we kind of characterize all the technology in layers, right? This is kind of down the bottom is the fabrications and the physics and circuits, RTL, this is gates, and on top of that, architecture, microarchitecture, ISA, this is the kind of RISC-V ARM, and those all the specification we're talking about. And also that's actually the interface between the software and the hardware, really the hourglass, narrow hourglass, the ways between the software and hardware. And on top of that will be more on application, the software side. So we'll see operating system and the program languages and algorithms and applications, right? So this is actually a full stack while we're teaching new students or for everybody who get into the field. This is how we teach them. So then we say, hey, why not just take this as a general classification, the rule of classification, and then break it down a little bit. So here is what we did, right? So this is where we're basically looking at the microarchitecture, right? So this is, we're basically picking a hypothetical CPU and draw the components, right? And within the CPU, basically CPU pipeline or CPU pipelines, and also put a bunch of peripherals like input, output, call processors, and caches, and a bunch of debugging auxiliary, components around it. So this is, we're kind of building this classification system purely based on from the perspective of a CPU designer, right? So you have each of the component will cover some certain area of your chip or certain area of your processor. This is just an illustration of the microarchitecture, right? So the other things would be very similar. So after we have proposed this classifications, we redo our classification, pattern classification for both MIPS and ARMS. Oh, great! No, we got a very interesting result right now. So again, we're picking the top 10 categories for all the patterns. And so if you look at the x-axis here, there are kind of really the categories. You look at here is the catch coherent, prefetch, branch predictors, validation methodology, and issue units, cache predictors. And those things are very informative for chip designers, for CPU designers. So for MIPS, it's scattered around all the patterns, scattered active patterns pretty well. So each category is very equally covers majority of their patterns. And for ARM, I would say this GPU, I wouldn't say it's an outlier because we're kind of at this moment focusing on the CPU, the core technologies, pipeline technologies. So we categorize pretty much all the GPU related patterns to a single category, right? So ARM owns Mali, right? So that's no Mali GPU. So everything falls into that category. But everything else, it shows up as very nicely, as very similarly to what we have for the MIPS. So initially having the MIPS, now we have the ARM. ARM is still, by the way, it's in progress data, but still the preliminary data shows we have a very good, classification methodology here. And also you can actually see the concentration of the patterns. So for example, for ARM, so you see lots of patterns related to the MMU. So this is the memory management unit translating your kind of virtual address to physical addresses. These are particularly useful while you're designing a large server chip. So this is, this is kind of where ARM is actually heading to. You can actually, by looking at this, you can see where active, or you get a sense, what kind of active development ARM is trying to get into. And also the other one's catch coherence. So this, I believe, so a couple of our students, although they're sitting here, they're kind of doing this pattern, searches and with KitLab all together. So this is, I think, where you can actually tell, ARM is actually strategically looking at this high performance stuff, even with, the third one, branch, right? Branch prediction is also a very must-have unit for high performance microprocessor. You can see ARM's, ambitious ambitions on high performance, microprocessor designs, but just by looking at this. So just by looking at this top categories, and then high performance, also look at here, they're probably typo here, but it's kind of low power technologies, right? So this is very efficient high performance processor. You can, based on their patterns, you'll see, you can tell this company is what this company is kind of focusing on, right? So what we call RIOS pattern classification methodology, which is the RPC, that is more informative than the MIPS and ARMS. Okay, so if you let me give you a very concrete example what RPC will look like, right? So this is kind of like pick a real US pattern. This is the pattern. I think this from one of the MIPS patterns talking about something with the MMUs. And this is, I think this is CPC, this is IPC. Under IPC CPC classifications, you can see IBC and CPC are very, very, very similar. But if you're looking at their top and second categories, although this is kind of something related with the MMU, like the memory management unit, they're not very informative, right? The top category is physics and the computing and or accounting. Uh, as a computer scientist, I don't know too much about the pattern just by looking at the numbers. But if you if you look at our classification, the RPC classifications, we put them under microarchitecture. It's very straightforward. It's a core technology. It's a CPU, not caches, not surrounding peripherals. And the subcategories is similar to the bottom, the leaf here. We're indicating clearly this is the MMU. So this is what we think. This is the excellent or more domain specific, domain friendly classifications. And if you also looking at the top two categories, right? So, or what we have here is we think the most important part is the microarchitecture, and the second one is the ISAs. Right? Those are the top categories that we think that has lots of patterns, in. So this is the quick stats from MIPS. You will see MIPS spend most of his pattern, like 40% of the patterns are with the CPU pipeline, CPU core by itself, and still some reasonable portion to the caches, right? Within the CPU by itself, within the core itself, we'll see very similar trend compared to ARM. The MMU and the branch prediction and those top function, those top categories are very very similar, right? So these are the kind of MIPS used to work on the server and works on the high performance the Unix server side, and they are having very similar pattern classifications. So ARM, I think you're having a very similar result here. But ARM, start focusing a lot more on the co-processor side, right? This is kind of, if you want to get more energy efficiencies, use a lot more a co-processor side. And you will see a very similar trend. And also you can see some like newer categories, interconnects. Those are very related to very, very large multi-microprocessor systems. You start seeing the increasing numbers in this interconnect. And unfortunately, I think as I mentioned, this is still work in progress. We haven't got the second level fully categorized yet. Given the workload of 3,000 patterns, we have to do that. There's actually, it's not very easy just looking at them using any of the tools and software. We have to go and look at them manually and check them, if it's correct. So at least there needs to be 6 eyes, something like that, looking at the same single patterns. So, but anyway, so this is also studying multiple instruction set architectures, a very good validations for our methodology as well. So we're getting a very similar result here. And also this is kind of increasing on co-processors. This is kind of increasing the trend on AIs and accelerators. So this is kind of something very interesting to when you build a product. And also ISA, is instruction set is, although RISC-V is open spec, but historically instruction set architecture is owned by a company or a single company. And also the company will try everything they could to protect this. This is the kind of for ARM, this is the thing they guard. This is, they can license you the right to use their ISA. You can build your own implementations, but you cannot change anything in the ISAs, right? For some company maybe a little bit different, but it's in general, it's very, very, very difficult to to change this. So this is why studying this is so super important. So when you look at the MIPS, like we said, they once interested in high performance implementations, the memory access instructions and floating point, right? FPU floating point performance very essential for high performance chips, and there are a lot of technology in there. Language translated instruction. This is when you start running business logic, running Java, running those like the JVM or your Android VM, they're kind of related technologies, right? So these are the the category. You can tell by using the RPC, you can actually see what are the really interesting technology to from the technology's perspective. And this is the ARMS characterizations. I think we have a very similar ones. To me, I'm kind of a little bit surprised. ARMS spent lots of patterns, lots of ISA patterns centered around the floating point instructions, right? They have a very significant amount of floating point instruction. I think partially probably related to the neon, they're kind of like the DSP signal processing engines. And also this is the kind of like the PAC-SIMD, that's the I think it's the real neon, right? So there's a kind of function unit for neon, and there's also the ISA for the neon. So this is something that really worth taking a look, a second look. So this is really, I think it's very interesting, showing where the company has focusing their protections, right? So the ARM put a lot of protection in the floating point implementations. That's kind of, I'm kind of a little bit surprised. This is the first time seeing this. And this is kind of number one category in their ISA patterns, right? Okay, and I think one of the goal is trying to make this open source, right? This is, we want this to be available and be accessed by everyone, and also we're definitely, other than the KWM, also looking for other collaborators, right? This is kind of joint development by two of the groups working very close together. But we have this already on the GitHub, right? So that you can actually download this and looking at our detailed classifications. In March, I think we did the first, the top two categories is R01 microarchitecture and R02, that's instruction set architecture. In April, we did open the remaining ones. Although we have less subcategories in this four categories, but I think they're actually in general, based on what been looking so far, think about the majority of them will be centered about R01, R02. There are not actually many things here, but moving forward, things might change. Like I mentioned, if you look at the Apple M1 processor, M1, M2 processor, really the secret is not really the high performance core implementation, but really centered around how they put up the SoC and their packaging technology, building a high bandwidth, high performance memory put in the SoC. So I think I'll be expecting there will be more patterns coming, in those areas that's falling into, 3, 4, 5, or 6. So, but anyways, we're kind of, this is still evolving, and we're putting under the most permissive license, BSD. I don't think anyone will sue us because for this. So I think BSD is probably the most permissive ones, and just feel free to use it and also contribute. We're also looking forward to any feedbacks. So when we start looking at patterns, I think pattern always associated with the lifetime of a company, right? So this is the reason, we start with the MIPS. It's not only we have, the chance to looking at the patterns from their whole company, but also, the MIPS has been pretty much complete the whole cycle, right? So MIP has been, so you can follow these timelines, right? This is from early incorporation, 1984, all the way to last year. MIPS has been, like I mentioned, has been sold to different companies, altogether 7 times, right? And to first early years SGI, and then later back to MIPS, and then to Imagination, right? Imagination is a UK company, and also we'll have a speaker from Imagination in the panel. And also around 2012, when MIPS sold everything to Imagination, although actually the business unit to Imagination, they actually start something called bridge crossing. ARM was also involved. It was also involved with the bridge crossing. Is really related to sharing kind of like the patterns, So that's actually a very interesting event. And actually, after that, because ARM paid a lot of more than 160 millions just in that deal. Eventually, ARM owns lots of patterns from MIPS, right? This ARM kind of strategically acquired lots of kind of classic important microprocessor pattern through that deal. After MIPS sold Imaginations, the business wasn't running very well, and MIPS has been sold to 2 other companies. First going back to MIPS by itself, and then to Wave Computing. That was a startup working on AI chip designs. But the company, because of financial issues, is kind of pretty much belly up right now, and they remaining entity called in short called Capital Finance is called Capital Finance Administration, but in short called Capital. Is kind of owning the kind of remaining patterns, right? So this is kind of really the lifetime of MIPS, and you'll see that the pattern is flowing around between different entities multiple times in history. Um, and also, bridge crossing is something really worth mentioning while we're looking at the company. I think this is a I think it's a very important event ARM has done in history, and also I think lots of classic important pattern has been throwing into that pool. So around 2012, so it's really what happened was it's kind of, I wouldn't say ARM like this, but ARM pretty much put the majority of the money, and along with 10 other members, all of them are pretty much working on the risk architectures, right? I think this is a little bit similar to when the OIN first incorporated, right? People are trying to create a pattern pool, and also there are members in this pool, and they all have this access to the patterns, right? This is including very notable ones, ARM, right? Apple, right? That's 2012, and that's even before Apple was trying to build their own Apple Silicon, right? So and Cavium, that's one of the early companies building ARM servers, and IBM, IBM Power servers, and Intel, IBM, they're kind of classic, processor companies, or companies making processors. That's really right to say it. Renesas, and it's from Car and Samsung, Sony, and more. I believe Qualcomm later joined that consortium, joined that club. So initially, I think they have close to 500, 490 patterns, MIPS patterns. And in the MIPS, so the benefit for the bridge crossing, the members is they kind of got protected. If you're part of the membership, right, you will not be sued by the MIPS, right? So this is kind of, create more like, think about this as a peace treaty, among all the members, and the MIPS, right? So MIPS will not sue these companies part of the bridge crossing. But unfortunately, when I talked to Pao from your nation, he has said the bridge crossing wasn't very quite successful. Even in the end, pattern trolls won't join this, but still, ARM was the leading members of the bridge crossings, and they spend over and more than almost half of the money just for the overall cash, just acquiring this like MIPS patterns. So, but later on, ARM has been strategically acquire all these patterns. So after that event, if you're looking at what are the majority of the assignees for the current MIPS patterns, so let's just probably focus on the active ones, right? You can see more than half of the patterns, those portion went to the bridge crossing is eventually owned by ARM, right? So ARM is actually the legal owner of those patterns, and the Capital just kind of getting the remaining ones. When I was looking at those patterns, I actually look at them one by one myself. They're pretty much think about it. They're kind of they're owning the majority of the patterns, right? So the most important patterns are actually belongs to the ARMs, right? ARMs has much higher qualities, and also we did very similar things for ARM. ARM kind of protecting itself pretty well. Most of them are still controlled by the major company, and there are also some sub entities from the ARM, and I believe there's some of the Finland that's kind of related to their Mali GPU business, but also some of the newer ones. So this slides what we're showing you here is the update number of patterns these two companies filed and also granted over the course of their lifetime, were from their beginning, pretty much. You can actually, by looking at the activity rate here, right? So there's one color, I think this is purple color is the pattern applications, and the green one is the grounded patterns, and also the dashed line, I think this is the ground rate for certain specific years. You can actually see the peaks, some of the peaks here, right? These are peaks corresponds to, I think this later it makes more sense because there are a lot more patterns felt. And even in the early days, MIPS was wasn't very much aware of the patents, and they didn't, it was not really in the game, so there were a very small number of patent filed. And later on, the up and downs really corresponds to, when the company that is business doing well is not doing well, has been sold to a newer company, and the newer company imagination start filing new patent, new batch of patents. So these are the kind of really, you can, by looking at this, you can actually see the activities of the company by itself too. So ARM, I think it's still going up. So looking at the trend, this is really corresponds to the takeoff there, the mobile business, right? They've been filing a lot more patents, but the funny thing is, the 2019 and 2020, I believe that's the cause of COVID. This is not really because ARM company is not doing well, but it will be interesting to see 2021 data and 2022 data moving forward. So if you're looking at the number of patents they have, this is the one from the MIPS, you can see, although in the bridge crossing back then was very important ones, but if you're looking at the patents, most of them will be expired pretty much soon in 10 years, but we still have 8 years, you have to worry about them. But after 2030, there are not much patent owned by ARM, acquired by MIPS, currently owned by ARM, will worry something. But on the other hand, the remaining entity, I believe this kind of later MIPS entity, they kind of own some patents. There's still some of them, right? So there's some of them you have to worry, but because the business is not doing well in the patents, they're kind of still dying down a little bit. But we see a very interesting cut here around 2030, right? So that's kind of the timeline. And also, if you look at subcategories here, so the microarchitecture one is still the dominant ones, right? So this is the most important category you should worry about. And then the ISA, there are many of them, they're still ranked the second, but there's that's kind of really the second important patent. So for ARM, unfortunately, we have to live with for the next 20 years. So this graph shows you, yeah, there's, actually the 2030, we'll still draw the line 2030, but but kind of looking at this, right, they have a very good patent portfolio, even from 2030 and 2040, and actually numbers actually increasing, not dropping. Right, so this is kind of corresponds to the ARM's business, and if you're in the microprocessor business, yes, you have to deal with ARM patents for the next 20 years, right? So that's a reality check. Okay, so this is probably among some of my last slides. This is the pretty much showing kind of really the plotting every single pattern. So although the single graph, there's lots of data. I apologize for the visualization here, but you can let me explain this to you. The x-axis here is number of independent claims per patent, and the y-axis here is number of citations per patent. So each dot represents a real patent. So the green ones is the ARM patents. The red one is the kind of patent, a MIPS patent, but eventually owned by ARM. This was in the bridge crossing batch. The blue ones are kind of really the ones by the capital. So you can really tell, you see lots of greens here, right? So, and also there's a very concentrated, the ARM is very focused, right? ARM doesn't have lots of patent with many claims, right? I've just most of them less than five claims, right? They have 5 claims, but they have a lot more citations than the MIPS patents, right? So this is kind of, the ARM kind of be the way they're kind of dealing with this pattern, they're kind of strategically defining high quality patterns over time, right? So this is kind of just from statistics. It's not, again, it's not a very good indication of how good the pattern is, but I'm sure by looking at US patents, this is a very good example of a company, how a company should build up your patent portfolios. Okay, so and litigations, right? This is when we did the first presentations last time in front of the RISC-V board. Chris Asanovich, my advisor, he said, it's more interesting to look at litigation around those patents, and then we did this. Right? Still, again, this is very early because litigation data is a little bit hard to get. So this is early results. We're checking MIPS, we'll start looking at ARMs. I believe there are a lot more ARM litigations. For MIPS ones, I'm not gonna explain each of the individual litigations, but what we summarize here is usually, MIPS and ARMS will, their litigation when they sue people, there's only, I think the goal is there's only solo purpose, right? They want to stop your business, right? They don't want you to, fight and, in the market, and so they want you to get the market share, right? So this is what exactly ARM and MIPS has been doing. And in some of the litigation cases, what we found is MIPS even, stop either one small company's business, and by trying, they resolve this, right? But as a result, the company will stop their selling their stuff, right? So this is kind of very, very serious, very, very interesting. This is kind of always tied to this like computations. And when we are looking at all the patterns they use, they're all related to microarchitecture and ISAs. Your instruction set, you're infringing on the instruction, infringing on the spec, and also infringing on the microarchitecture, infringing on implementation, right? So these are the top two litigations, or that's why they're worth a lot more attention, right? Okay, so I will conclude my talk, I think. So I talk about, pattern classifications. This is kind of really domain knowledge based, domain knowledge driven approach. And also we're trying to make this open source effort, looking forward to collaborators in this field. And we are doing a lot more hard work on ARM, and we really want to do x86. Right? This is, there's no way you don't do x86. I believe we'll have more, findings next time. And also we haven't really looking at the China effort at this moment yet. We're trying to look at the US patterns, which has more regulated, it's more standards there. But at some point we're going to look at China. That's because we're in China, we're dealing with the this China supply chain all the time. We have to look at it. Okay, so with that, I'd like to conclude my talk, and also thanks the great effort of all the team and all the hard work. So, and I'll be happy to take any questions you have.
Oh, thank you, Professor. That's really impressive. My question is, from your perspective, what kind of technical field is most likely to be exposed to the threat of patent litigations in the context of RPC?
Okay, so I think the question is about what technical side would be more vulnerable. I would say, so that the thing we found, like just like I mentioned very early this morning, those radioactive areas, and also those areas has already been tried by incumbent, right? So for example, cache coherence, right? This is a kind of multi-processor technologies, right? We're start seeing in the past, right? Only the like high performance ones, like the very expensive machines had this, very advanced technologies, right? But nowadays we're start seeing the same technology goes into your phone, same technology goes into our, even your IoT devices, right? And this is kind of, really the very beginning, like mentioned, we're so determined to do this because we're really bumping into this in our real, open source effort, real design. Although we look at some of the ARM designs, but we design our own, but, then we start looking at the patterns, oh no, that's people have tried this before. And also there are also other funny stories is my students looking at all the cache coherent patterns, they were finding that Intel doesn't actually own lots of cache coherent patterns. Instead, they license a lot of patterns from IBM. So those areas used to be owned by high performance HPC and supercomputers. I think will be much easier to have a patent infringement there, because there are not a lot of textbook designs. We do have the basic principles, but all the implementations are pretty much proprietary. Anywhere you have proprietary implementations, that's where you should pay attention to, and especially for those companies like IBM, right? Those companies, those like very mature, I would say, old companies. They technically they put patterns already there, so you have to be really, really careful.
illustration of a patent research report, different different from just different to engineers report, and different to just the patent attorneys report, but more than engineer, more than patent attorney. So thank you. While regarding RISC-V, and I remember Crystal mentioned, the chairman of the board mentioned RISC-V is not just open source. There are also many commercialized license. So regarding the RISC-V program, what about the strategy of patent creation and also the later policy regarding patents?
Yeah, I think that's a very good question. I think we're among the few entities, right, or that's realized could be an issue, where other people has been realized this is an issue. This is why the RISC-V International RISC-V Foundation start working with OIN. So OIN has already have a protection club. Right? So if you join the club, nobody can sue each other, right? Or as club members cannot sue each other. But there's some of other open source organizations, for example, Chip Alliance, they probably don't have this term in their member agreement. I would say for this really goes back to the business side of the RISC-V, right? I don't think people are really ready yet to get into really the high performance, high performance zone. Lots of designs in the past are kind of more like IoT, and so one thing is there's not a lot of money going there, so there's no point of suing people because there's not much incentive, and people haven't really realized that. But there are some companies have been strategically looking at it, and Google, I believe, and also Alibaba, they've been talking to OEMs, and also they're kind of very active in the field as well. I think people will start noticing this, and this is the reason why we're having this workshop and having people discussing this, right? I think this is so in the past year, I think the majority, because there's the RISC-V International kind of moving from the historical reason, moving from outside the US to Switzerland, right? And people have been worrying about the user agreement and all the other things, haven't got the bandwidth really looking at the real things that really money matters, right? But once we start seeing more high performance design these days, for especially built with RISC-V, you'll be start seeing the litigations. You'll be start seeing, and also I believe Western Digital also sue someone using someone else's patent, but that's kind of very typical approach in this community. So there are litigations already. So it's a real problem. Okay, so there's someone online. Okay, can you just read the question to me so that that'll be easier. Thank you. Okay. Okay, that's a more like a general question. I'll repeat that in English. The question is, how does patterns from MIPS and ARM affect RISC-V? I would say not just a single pattern, right? It's just like systematically, you have to understand what are the patterns, not just even MIPS and ARMs. I would say it's in broader sense, right? There's kind of, you have to look at the patterns, NVIDIA patterns from x86, right? They all relate to the implementation. If you want to build implementations, the implementation is usually easier to be patterned, right? You cannot patternize. ISA can still pattern that, but given we already know RISC-V ISA is kind of free of any legal issue, right? That's we can guarantee. We have done lots of studies, and there have been lots of lawyers have been looking at this. I think there's nobody will have some issue to sue RISC-V International the infringement on the ISA, but MIPS and ARM, they do matters. What matters is the microarchitecture and the implementations. Right? This is why we're starting this, looking at all these microprocessor patterns. Okay. All right. I think that's pretty much it.